Okay, so hello everyone and welcome to today's edition of our extremal and probabilistic combinatorics seminar. Before we start with today's speaker, let me quickly go through the usual stuff, so technical stuff. During the talk, the best way to ask questions is via the chat. You can find buttons for the chat, I think, on the bottom of your screen. Our speaker told me that he has two screens and he will be most likely able to follow the chat, but if not, then I will interrupt him if there is a question. Also, you will find his slides on our webpage. So in case you want to open them in a separate window, then you can easily do so. And there will be space for more discussion at the end. What we usually do is that we have sort of official Q&A session after the talk, and then if people want, we switch off the recording, and there is some more space for informal discussions. Okay, so now it's my great pleasure to introduce Matthew Kwan, who will be talking about extension complexity of polytopes. And we particularly appreciate Matthew agreeing to give his talk because Matthew is based at Stanford, so it's 6 a.m. for him right now. So please go ahead, Matt.
Thanks, Jan. Yeah, thanks to the organizers for inviting me. It's a great pleasure to give this talk. Yeah, so as Jan said, I'll be speaking about extension complexity of low-dimensional polytopes, and in particular with some joint work with Lisa Sauermann and Yufei Zhao. Yeah. So first I should say that this topic, extension complexity, is not really the sort of thing that maybe might usually appear in a seminar on extremal and probabilistic combinatorics. It's not something that any of us really knew very much about before we started working on this project, and still we're far from specialists, so if I say anything that is ignorant or mistaken, I hope you can forgive me. Yeah, so that's yeah. So I'd like to introduce this topic in probably not the most, well, definitely not the most natural way, but let me tell you how we began to get involved in this area, which is that we were looking through some lists of open problems from various workshops, trying to find something new to work on, and we found this quite intriguing question in the open problem session of a 2013 Oberwolfach workshop. So let me remind you what rank is. I guess you probably already know that the rank of a matrix is the smallest r for which there is a matrix factorization m equals tu, where t has r columns and u has r rows. And there's this variation, or the slight variation of the notion of rank called the non-negative rank, which is, again, it's the minimum r such that there is a factorization m equals tu, where t has r columns and u has r rows. But in addition, you demand that both t and u, all their entries are non-zero. So this is I mean, it's a definition you can make. So this is clearly, it's only going to make sense when M itself has non-zero entries, if you want this factorization to be possible. But if M does have non-zero entries, you can always do this, because in particular, you can choose the trivial factorization here, where M equals M times the identity matrix. Okay, so that's a definition. It raises lots of questions. Maybe the most fundamental question is whether this is actually different from the ordinary notion of rank. Meaning that if you have a non-negative matrix and you're trying to factorize it, does it actually help to use negativity in the factorization? And that's sort of the direction that this question is about. So this is a question that we found in the report in the conference report of this workshop. I wasn't there, but apparently it was asked by Nati Lineal whether there exist matrices whose rank is bounded, but whose non-negative rank is enormous. is linearly large in the dimensions of the matrix. Yeah, so basically it seems here that the right question is not whether the rank can differ from the non-negative rank, but rather whether the rank gives any control at all over the non-negative rank. So it's easy to show that if the rank is 2, then the non-negative rank is also 2. But beyond that, could it be possible that the rank can be 3 and the non-negative rank can be n? Okay, so we found this problem, which sounded quite interesting. At the time, I had no idea what non-negative rank was really about and why the motivation for this question. But I did think that I know how to prove things about random graphs and random matrices, and maybe the way that you should try to prove this is by considering a random matrix, because I mean the property of having small non-negative rank is kind of like saying your matrix is well structured. If you'd like to avoid that, maybe I should choose it randomly. So as a very naive and specific example, maybe I should consider a random 0, 1 matrix and condition on its rank being 3. Maybe that would be a way to prove this, or to confirm this question. So it turns out that this doesn't really have any chance of working, and this was way too naive. But before I tell you about that, and before I sort of tell you about some of the context of this problem, this problem has some background. This wasn't really invented by Nati. He was just sort of sharing the problem. But before I tell you about that, I want to tell you about a seemingly completely unrelated question. So I've told you about the Overfuck problem sessions is an interesting source of open problems. Another interesting source of open problems is this thing called the Open Problem Garden, which is this website that collects open problems. And here is one of the problems we found on their website. They define the extension complexity of a polytope to be the minimum number q for which there exists a polytope with q facets, polytope q with q facets and an affine mapping pi with pi of q equals p. Yeah, so maybe I had better define. So in case you have forgotten a polytope, what that means is that it's a region in Euclidean space, a bounded region in Euclidean space that is the intersection of finitely many half planes. So each of the half planes like chops off like a hypersurface that's called a facet. So as an example, conveniently, the logo of this website, this is a polytope in 3 dimensions. And in the picture, you can see 6 facets of this thing. Okay. So this definition, what it's trying to say is that for my favorite polytope, is it possible to represent my polytope as an affine image, or you can think of just as a projection of a polytope in higher dimensions, but which has much fewer facets. So here's a picture which may help to understand that this definition actually is meaningful. So this is a picture of like the shadow of a polytope on the floor, a 3-dimensional polytope on the 2-dimensional floor. So the shadow is a regular hexagon, which is a 2-dimensional polytope with 6 facets. But despite the thing having 6 facets, we're able to realize it as a projection of something with only 5 facets. This triangular prism thing has just 5 facets. Yeah, and it's not possible to do it with fewer, so that shows that the extension complexity of a regular hexagon is 5. Anyway, so the question that was being asked is it possible to find, or does there exist a polygon, a 2-dimensional polytope, whose extension complexity is linear in n? In other words, is it possible that sort of this taking things into higher dimensions and projecting down doesn't really help you very much? That's a question. And just like for the other question, this kind of property of having bounded extension complexity, it's like saying your polytope is quite structured, perhaps. So maybe a reasonable way to try and prove this is to consider a random polygon. So this was also suggested. What is the extension complexity of an n-vertex polygon whose vertices are drawn randomly on a circle? Okay, so that's 2 questions. The first question was saying, is there a matrix whose rank is small but whose non-negative rank is enormous? And the second question is saying, is there a polytope whose dimension is small, whose dimension is just 2, but whose extension complexity is enormous? And surprisingly, or maybe not that surprisingly, given the way that I've set this up, these are actually basically the same question. Due to this connection that was, I think, quite famously proved by Yannakakis, he proved that the extension complexity of any polytope is equal to the non-negative bound of any slack matrix of the polytope. So I should tell you what a slack matrix is. So it's what you might guess. So polytope is an intersection of finitely many half planes. Each of those half planes is really a linear inequality, a constraint, meaning that all the points in the polytope satisfy that constraint. Some of them will satisfy it sort of tightly with no slack, and some of them there'll be some slack. So if you consider all the vertices of the polytope, and you consider all the slacks of the vertices with respect to the facets, you can encode that information in a matrix with rows given by the vertices and columns given by the facets, and that will that's the slack matrix. So Yannakakis showed that computing this extension complexity thing is the same as the non-negative rank of a slack matrix. So here's like a sort of a dictionary translating between the two worlds. So as I said, the rows of the slack matrix correspond to the vertices of the polytope, the columns correspond to the facets. This theorem says that the non-negative rank corresponds to the extension complexity, and it is also not very hard to show that the rank of the slack matrix is equal to the dimension of the polytope plus 1. So this explains the significance of 2 and 3 in the first in the two questions I started with. Having a polytope with dimension 2 and a polygon is the same as having a matrix with rank 3. So there's a pretty obvious connection between the first two questions, trying to find a gap between rank and non-negative rank, or dimension and extension complexity. Yeah, very good. So that is my, someone says in the chat, is the lower bound of 5 obvious? Right, I don't think it's necessarily obvious, but it is true. Yeah, so that's a brief introduction to these concepts. I should maybe say a little bit about why anyone would care about these definitions. I think that extension complexity is an important thing in combinatorial optimization because it's not hard to imagine that if you're trying to optimize something over a complicated polytope, you'd be very happy if your complicated polytope was secretly a projection of some higher dimensional thing, which was much simpler, because then you could optimize over that. And apparently, according to some, well, apparently the notion of non-negative rank is also interesting in statistics and machine learning, apart from its connection by this theorem to extension complexity. Okay. Very good. So the types of questions that I will be interested in this talk are sort of extremal and probabilistic questions connecting the extension complexity of a polytope to sort of the basic parameters of the polytope, or nearly equivalently trying to understand the extension, the non-negative rank of matrices in terms of the basic parameters of a matrix. So on the slide, I have some simple bounds. So the first simple thing you can observe is that the extension complexity is always trivially at most the number of facets of the polytope. It's also not hard to see that it's also at most the number of vertices. You can either see that with this Yannakakis theorem or using this thing called the dual polytope. There's this operation called the polar dual, which sort of flips a polytope into its dual, swapping the role of vertices and facets without changing the extension complexity. Yeah, so from the point of view of extension complexity, vertices and facets are basically the same thing. Okay, that's an upper bound, and a trivial lower bound, or a simple lower bound, is that you can't work miracles, and the extension complexity is always at least the log. This is the log base 2 of say the number of vertices. Yeah. So this is also easy to prove. I think it follows from the fact that if you have a polytope with n vertices, the number of faces of all dimensions is at most 2 to the n. So there's obviously a pretty big gap between both of those bounds. I think you can't do any better in general. But so we should start introducing some more information about the polytope, namely the dimension. So a third trivial bound is that the extension complexity is always at least the dimension of the polytope plus 1. And that's just because the number of facets in a polytope of dimension d is always at least d plus 1. A simplex attains the minimum there. Okay. And so then when things, so all these are pretty trivial, but where things really start to get interesting is when you start to ask about upper bounds on extension complexity in terms of the dimension, which is really what these questions I started with are getting at. So here's sort of re-asking basically the question that already appeared. What is the, if you know the dimension of a polytope is d, what is the maximum possible extension complexity it can have? This is a very extremal type of question. And I think it's also interesting both to understand the extremal question and intrinsically to understand what happens generically. So if I have some notion of a random polytope or a typical polytope, and I know its dimension, well, a random polytope of dimension d, what is its extension complexity going to be? So these are two questions that I am interested in. I think for both of these questions, it is plausible to believe, and this is sort of more or less the belief that was appearing in these first two questions, it's plausible to believe that this question is not a very good one because the dimension tells you essentially nothing. I think one may believe that even if you restrict the dimension as much as you can without making things trivial, so even in the two-dimensional case, it's plausible that not only does there exist a polytope with extension complexity n, but this is the generic behavior. I mean, I think it's actually pretty natural to imagine that the answers to these two questions are about the same. That if you want to have maximum possible extension complexity, the sort of generic case should be worst. So it's plausible to believe that the trivial upper bound that holds independently of dimension is also, it could also be that bad, even if you have a lot of control of the dimension, which would make this a not particularly interesting question. So it turns out this plausible belief is false, but let me tell you that along with some of the other history of this problem, which I've neglected until now. Yeah, so I want to reiterate that I'm not a specialist here, and if there's if I forget or I'm ignorant of something that I should have mentioned, I do apologize. Maybe you can let me know in the chat if there's someone here who does know. But as far as we could tell, the first time these types of questions had been considered was in a paper by Beasley and Laffey, where they're actually considering non-negative rank for its own sake, but here are some sort of translations of what they did into extension complexity. So they proved that there exists an n-gon, two-dimensional polytope with n vertices, which has extension complexity log n, so at least getting some separation between dimension and extension complexity. And I think they were the first to conjecture this thing that the extension complexity could be as large as n, even if you restrict the dimension to 2. Okay, this next thing, this actually appeared on the first slide, but I didn't mention it. So as far as lower bounds go, it was proved by Fiorini, Rothfuss, and Tiwari that in some sense, almost every n-gon has extension complexity at least of order root n. So this is actually still the best lower bound that is known in the two-dimensional case. They prove that if you have a polygon whose vertices satisfy some general position type condition, then you get some pretty strong lower bound on extension complexity. But of course, it's still much less than this conjecture. Okay, the next thing that happened was that independently, Shitov and Padrol and Pfeifel, what is the quantification of the dimension in the theorem / conjecture? So I wrote here n-gon. N-gon means two-dimensional polytope with n vertices. So the quantification here is the dimension is 2. Yeah. Yeah. Okay, so Shidov and Padro and Feifel managed to prove a non-trivial upper bound on the extension complexity of 6n/7. So this disproves Baselian-Laffey's conjecture. Of course, it could still be that the extension complexity can be linear. So it's sort of only slightly a non-trivial bound, but it does disprove this conjecture. I should mention that this Shitov is actually the same Shitov who disproved Hedetnemi's conjecture recently. So it's a name I guess we are already familiar with in extremal combinatorics. Anyway, so you can get some non-trivial control, some sort of weak non-trivial control if you know very strong information about the dimension. But shortly after this, Shitov managed to sort of disprove this conjecture even harder, proving that if you have a two-dimensional polytope with n vertices, the extension complexity is actually sublinear in n. I think the bound is something like n over log n or something, but still it's okay. So I mean, so this proves that the situation is genuinely interesting. The dimension does tell you something. So these kinds of questions are worth studying. Okay. So I should also mention that I guess the reason this parameter is interesting is because it might allow you to simplify combinatorial optimization problems. And so a lot of the work, maybe even, well, the majority of the work really has gone into studying specific polytopes that are of interest in combinatorial optimization. Things like the traveling salesman polytope or the perfect matching polytope or and so on, which I won't say too much about because it doesn't have very much to do with what I'm talking about today. But let me just highlight one particular theorem, which is of sort of extremal interest, which is that Keibel and Weltke proved that there exists a polytope called the correlation polytope, whose dimension is quite small in terms of the number of vertices. So it's low dimensional polytope, but which has very large extension complexity. So this is also some sort of lower bound in some regime of the extent to which the dimension could possibly control the extension complexity. Okay, and just a few other things. So it was proved by Padrol, a generalization of this Fiorini-Rothfuss-Tuari thing to higher dimensions. He managed to prove that a generic for any d, a generic n-vertex d polytope has extension complexity at least of order square root dn. And then finally, the most recent thing that happened was that earlier this year, very recently, Shitov managed to even further improve his bound on his upper bound on the extension complexity of an n-gon to n to the 2/3. So a lot now is known about the two-dimensional case, but actually there's no non-trivial upper bound known for any class of polytopes in dimension 3 or higher. Okay. Okay, so that is some history. Let me now tell you about our results. Okay, so the first thing we were interested in is the random case. So if I take a random polytope, what is its extension complexity? Now there's actually no sort of uniquely most obvious way to define a random polytope, but here are two of what I think probably the two most natural ways you might want to define a random polytope. So you fix your dimension. This is for a constant dimension, by the way. You fix your dimension, consider the unit ball in that dimension, and you can either pick a bunch of random points on the surface of the ball, on the sphere, or you can pick a bunch of random points, randomly independently chosen on the interior of the ball. And in either case, you can take the convex hull of these points. So those are two quite natural ways to generate a random polytope, and we proved that for both of these notions, the extension complexity is typically of order root n. where here this big theta encodes both an upper bound and a lower bound. So the lower bound was previously proved by Padrol on the previous slide, but the upper bound is what's interesting here. So maybe just to say something about these two models. I mean, so the advantage of the first model is that if you take any number of points on a sphere, they're always going to be in convex position. So this first model is going to have exactly n vertices always. And the second model, if you're taking, if you're taking points in the interior of the ball, they may not be in convex position, and you have to do some work to find out how many random points I should choose in order that I get about n vertices and facets. But this is the answer. If you choose n to the d+1 over d-1 random points, then you're going to get about n vertices and facets. Yeah, so this first model is the one that has been considered in connection with extension complexity before. And this second model, well, so it turns out we sort of discovered as we were working on this that in probability theory, there's this field of random polytopes is actually rather enormous. And there's a lot of work on random polytopes, and they seem to prefer this. There's certain reasons why they prefer the second model. So we thought, let's also consider that. One advantage of this is that a lot of this work in extension complexity has been interested in sort of the generic situation. If you have points in general position, like if you have a polytope whose points are in general position, and if you constrain everything to lie on the sphere, you could argue that's not really in general position. But no matter how you might sort of try to define general position, this second model is probably going to do it. So in particular, no bound better than root n can hold for all polytopes whose vertices are in general position. Okay, so we know what happens in the random case. We get a bound of order root n, which maybe suggests that the extremal answer, the answer to the extremal question, is also of order root n in the worst case. Maybe a bit more evidence for that is our next theorem, which is this going back to the two-dimensional case. If you have a cyclic polygon, meaning you have a polygon whose all vertices are on a common circle, then you have the same upper bound. The extension complexity is bounded by constant times root n. So this is proved with a very similar proof to this. This proof is quite flexible, but unfortunately we weren't able to figure out how to get this proof to generalize to every polytope, but at least it does work for cyclic polygons. Yeah, so it seems that if you fix a dimension, then the extension complexity must always be rather small, maybe of order root n. But as a result in the other direction, our last result is that if you allow the dimension to grow with n, even to grow quite slowly with n, so if the dimension is of the form n to little of 1, you may lose control over the extension complexity. So the extension complexity could be as large as n to the 1 minus little of 1, even if the dimension is of the form n to the little of 1. So maybe this is not terribly surprising given the result on the correlation polytope on the previous slide. But that is, so this in some very, very weak sense confirms this plausible belief that the dimension beyond a certain point, the dimension is not telling you much about the extension complexity. Okay. Very good. I would like to spend the rest of my time telling you about the proofs of these things. And in particular, I'd like to talk about, well, first, I'd like to talk about the third of these theorems here, about the existence of a polytope with low dimension, high extension complexity, because it's basically completely combinatoric. Actually, all three of these proofs are very combinatorial, especially the third. Okay, so let's talk about that. Okay. So using this theorem of Yannakakis, if I want to prove something about polytopes, it's basically equivalent to prove something about matrices. So it turns out that it's sufficient to prove that there is a matrix whose ratio between the non-negative rank and the rank is of order n to the 1 minus the log of 1. It's not completely obvious how to use Yannick-Ucker's theorem to get the other thing from this thing, but it is possible. Yeah, and I should also mention that this question is of independent interest about non-negative rank, and this answers a question that was asked by Hrubesch. Yeah. Okay, so okay, so if we want to prove this theorem, this parameter of non-negative rank is not a very combinatorial quantity. So I want to bound the non-negative rank in terms of a more combinatorial quantity called the biclique covering number. So let me make some definitions. So for any matrix, I'm going to define the support graph to be a bipartite graph with a part corresponding to the rows and a part corresponding to the columns, where I put an edge if the corresponding entry of the matrix is non-zero. And I'm going to define a biclique covering to be a collection of complete bipartite graphs in the support graph. That is to say, a collection of bicliques, which collectively cover all the edges of the graph. And then the rectangle covering number, or equivalently, I mean, two different names for the same thing, the rectangle covering or the biclique covering number, is just the minimum number of bicliques in a biclique covering. And the point of this is that we have a lower bound on non-negative rank. It's always at least the rectangle covering number. So if we want to show there exists a matrix with high non-negative rank, it suffices to worry about this biclique covering parameter. Yeah. So this lemma is very simple, almost trivial. Maybe you already see how to prove it, but because it's so simple, I'm going to quickly tell you the proof. So here is why the non-negative rank is always at least the rectangle covering number. Basically, the point is just that if you have a non-negative factorization, you can produce from that in a very simple fashion a biclique covering. Okay, so let's consider, let's let R be the non-negative rank of the matrix and consider a minimal non-negative factorization of that matrix. And then using that, I'm going to define sets AI and BI. So for each I is a set of rows of T such that the ith entry in that row is non-zero. And BI is a set of columns of U such that the ith entry in that column is non-zero. So the rows of T are in correspondence with the rows of M, and the columns of U are in correspondence with the columns of M. So this is really a set of rows and columns. It induces some subgraph of the support graph. And it's not very hard to check that each of these is going to induce a biclique. And collectively, these bicliques are going to cover the support graph. Basically, this is just due to the fact that when you add together a bunch of non-negative numbers, the sum is going to be non-zero if and only if all of the terms are non-zero. This is a nearly trivial thing to check. And that proves this bound. Okay, so with that in hands, in order to prove this thing about matrices, it suffices to show there exists some matrix, some n by n matrix, with many non-zero entries, which has small rank n to the little of 1, such that the largest biclique in the support graph has at most n to the 1 plus the little of 1 edges. So if the largest biclique is small, then in a biclique covering, you're going to need a lot of bicliques. So this is really a lower bound on the biclique covering number, which, I mean, we'll prove this. Okay. And so the matrix that does this is really simple. Here's what it is. So I'm going to define G to be about log n, M to be about root G, and I'm going to let Q be the set of all multiples of M which are at most G. So the intersection of the multiples of M with this set. And then my matrix is just going to be, well, so it's going to have rows and columns indexed by binary vectors of length G. So because G is about log n, so this is basically an n by n matrix. And the xy coordinate for binary vectors x and y is just the product over all multiples of M, over all Q and Q, of the dot product of x and y minus Q squared. Because I'm squaring this, it's a non-negative matrix. And by design, the entries are going to be non-zero precisely when the dot product of x and y, well, the entry is going to be 0 precisely when the dot product between x and y is a multiple of m. And of course, a binary vector of length g is really the same thing as a subset of the set 1 through g. So in that language, dot product corresponds to intersection size. So we should think of the rows and columns as being indexed by sets, and the entry is non-zero when the size of the intersection of the two sets is a multiple of m. So certainly it is true that this thing has many non-zero entries because it's going to have a non-zero entry whenever you're not a multiple of m. Well, it's not hard to show that typically, I mean, things are relatively well distributed mod m. It's also not very hard to show that the rank of this thing is small. So this is more or less just because if you expand out this product here, you get some polynomial, and the number of terms is not very large. And this expansion into a sum of monomials, this polynomial is basically corresponds to a factorization of the matrix. It's going to have negative signs in it, so it's not a non-negative factorization, but it's not very hard to show that this thing has small rank. So we just need to show that the largest biclique in this thing does not have too many edges. The largest biclique in the support graph of this matrix does not have too many edges. And that's actually an extremal set theory question, because what it means to have a biclique in this matrix means you have a set of rows and a set of columns such that all the corresponding entries are non-zero. So a set of rows and a set of columns is like having two set families, two collections of sets, two collections of subsets of 1 through g. And you know that all the cross intersections, all the intersections between a set in one and a set in the other is not a multiple of m. And so the question is, how large can be a pair of set families with that property? And yeah, that's the sort of thing that people study in extremal set theory. So this is a variation. So there's this restricted intersection theorem that was famously proved by Frankel and Wilson. And this is basically a cross-intersecting version of that. So it is known, proved by Zhao, that if you've got two set families, and if their cross-intersections are restricted mod m, meaning you have some proper subset of all the residues mod m, such that the intersection sizes always fall in that subset, then you have some bound on the product of the sizes of these two set families. So the product of the size of the two set families is basically the number of edges in the biclique. So there's a very close correspondence between these two things. So I've not written exactly the formula that's in Scull's theorem, but maybe without thinking too hard about the numerology, let me just say that this does give you an upper bound of n to the 1 minus little o, n to the 1 plus little o of one of the number of edges in any biclique of the support graph. Okay. Yeah. So that is, I mean, up to this theorem of Scull, that is more or less a complete proof of the third of our theorems, that there exists a polytope with low dimension and high extension complexity. So I'd like to also very quickly say a little bit about the other of our, well, of one other of our results about random polytopes. There's also, I think, some interesting ideas there. So yeah, so the setting was that we had a random polytope, meaning, for example, we have a sphere, a fixed sphere, and we take a bunch of random points on the sphere and we take their convex hull. So let's just say that I have a polytope whose vertices are well distributed on the sphere in some suitable sense. I would like to prove the extension complexity of this thing is upper bounded by root n, which is the same as proving that the slack matrix has non-negative rank upper bounded by root n by Yannakakis's theorem. Okay, yeah, so I've got the slack matrix, the columns correspond to the vertices, and the rows correspond to the vertices, and the columns correspond to the facets. Okay, so I will really just sketch some of the ideas of this proof, but maybe the most, or one of the most crucial observations is this, which maybe would help to show you the version of this with a picture. But it's an observation that whenever you have the situation, you have a polytope vertices well distributed on a sphere. If I consider some sort of small patch of facets on the sphere, so here, like near the top of the sphere, I've got this small blob of facets. And if I have some set of vertices v primed, which is well separated from this patch. So for the, what does the well distributed mean? Are the points and vertices picked independently? Yeah, so in the theorem statement, yeah, my random polytope is obtained as the convex hull of some independent uniformly random points on the sphere. Here for this proof, I'm just considering some vague notion of what well distributed means. This will be only a very vague sketch anyway, but just to try and show that this proof is quite flexible and does not really need this independence or uniform distributedness. Anyway, yeah, so you have the situation where you have a bunch of vertices which are far from the patch. And for concreteness, let's say that the vertices are at least 10 times as far from the patch as the diameter of the patch, say. So then this observation says that if you consider the submatrix of the slack matrix, where you take just the rows in V primed and the columns in F primed, then the non-negative rank of the submatrix is going to be bounded. So some version of this was first observed by Shitov in a two-dimensional case, and we pushed this to high dimensions. Okay, so that is a fact. Why is that true? Well, the proof is not short, but I think I can show you the idea with a picture. So here's roughly speaking why this is true, because under these conditions, I can define what I'll call a polyhedral lampshade, which is some polytope with a small number of vertices, with a bounded number of vertices, such that the whole polytope satisfies all the constraints corresponding to these facets in F primed. So if you extend out each of these facets at the top to a hyperplane, it will be on, this lampshade will be on just on the same side of all of these hyperplanes. And such that this lampshade thing contains all the vertices in V primed. So this is possible because we only considered some very small patch of facets near the top, which is almost flat. Yeah. So this property of obeying all the F prime constraints basically just means you're below some level with a little bit of sort of downwards pointingness because the facets are, anyway. So with this observation, the lemma follows fairly straightforwardly. The point is that for each of the vertices in this lampshade, so there's not very many of these vertices, I can consider the vector of slacks of V with respect to all the constraints corresponding to the vertices in F primed. There's not too many of these vectors. And then, so each of these vectors is non-negative because the lampshade is on the correct side of all the facets in F primed. And then I observe that because each of the points in V primed is inside the lampshade, is in the convex hull of the vertices of the lampshade, that implies that every row of the slack matrix, or every row of the submatrix of the slack matrix, is a convex combination of these special slack vectors. And that's just because the slack vector, or really the slack function with respect to a facet, is an affine linear function. So it respects convex combinations of things. Yeah, so if you use these slack vectors in addition to the coefficients of the convex combinations, they basically give you a non-negative factorization of bounded size, proving this thing. Okay, so that's what I just said, and then the idea of the proof. Well, okay, I'm running out of time, so anyway, I only plan to be extremely vague. Here is the strategy for how we would prove this. So we know how to, if we have a single patch and we have some vertices far from the patch, we know what to do. So I'm going to cover the entire sphere with small patches. So every facet is contained in one of these patches. And in doing so, I divide the slack matrix into submatrices, into block submatrices, where for each pair of patches, I consider the vertices in patch A versus the facets in patch B. The submatrix of the slack matrix correspond to those vertices and those facets. So I divide the whole thing into a bunch of submatrices. For some of those submatrices, I'll be considering vertices far from facets, and in which case I get to apply this lemma and show that the non-negative rank is bounded. But there will be a small number of exceptional blocks where I happen to pick a patch A was close to patch B, and I don't have this well separated condition. I don't have any control over its non-negative rank. So I can cover the slack matrix with a bunch of matrices which mostly have bounded non-negative rank, but some of them don't. And then to be extremely vague, then what we do is somehow we deal with the exceptional blocks separately. We have some sort of operation, some sort of modification of the slack matrix, which sort of slightly perturbs the slack matrix and somehow fixes the exceptional blocks in such a way that it doesn't do too much damage to the non-negative rank of the other blocks. This is quite related to an idea that Zhao did in one of his papers on the subject. So I don't really want to say too much about why this is possible, but maybe the key thing you should realize is that if you look at the entries of both of these blocks, like the exceptional blocks or the non-exceptional blocks, the size of the entries in the exceptional blocks is just much smaller. Just because the exceptional blocks consist of slacks of vertices close to facets, and the non-exceptional ones is vertices far from facets. Meaning that if you'd like to sort of make some change to fix the exceptional blocks, you don't need to, the changes you need to make are quite small compared to the entries in the non-exceptional blocks. And this thing about the lampshade on the previous slide is fairly robust. If you jiggle the points around, it still works. I mean, that was very vague, and it was featuring several lies, but that's all I really want to say about the proof of this upper bound in the random case. And I have 1 minute to give you some open problems, to discuss some open problems. So here are, I think, some interesting open problems. The first one is that it would be nice to actually properly resolve the answer to this extremal question. Especially if I fix the dimension D and I have an n vertex D polytope, is it always true the extension complexity is bounded by root n? Or what is the right answer? And no non-trivial bounds are known yet in any dimension other than 2. So that would be, I think, very interesting to prove even a sublinear bound in higher dimensions. The second question is, I mean, related to this third of our theorems. Like, how large can the dimension be before you lose all control over the extension complexity? So we prove some version of something like this with a little of 1 in there, but here this is a more exact question. I don't know what the answer to this question is. And finally, there's the question about non-negative rank, which again is quite closely related. How large can be the ratio between non-negative rank and rank? So we saw the answer to this is n to the 1 minus little o of 1. Because that little o of 1 is in the exponent, I think it would be interesting to understand this further. And in particular, I would be quite interested in whether randomness helps for this question. Because, I mean, there's some intuition that choosing things randomly should help to find something with no, if you want to avoid having low rank. But we didn't know how to prove anything using randomness. And I mean, the example that we had was completely explicit. Yeah, so that's all I wanted to say. I have some questions in the chat. Q1 even, is it known that for D equals 3, no. So in the 3-dimensional case, literally nothing, as far as I know, is known. So even a bound of n minus 1 would, I mean, I think would be interesting. Yeah, so I hope I've convinced you that there are some interesting questions here for extremal and probabilistic combinatorialists. But that's all I wanted to say.
Okay, so if you are done with your talk, which is my understanding, so people can just unmute themselves if they want to applaud, which I think this talk really deserves. And please, if you are unmuted and you have a question, then just go ahead with your question.
Could I ask a quick question?
Certainly, yeah.
Yeah, so in general, rectangle covering can be quite far from non-negative rank as well. So do you know if maybe you can get more in your proof if you actually used something more sophisticated like this hyperplane separation bound or something closer to non-negative rank?
Yeah, so we did think so. So I assume you mean for this theorem about separation between
yeah.
rank and non-negative rank. So I mean, the particular construction is designed specifically for rectangle covering number. Yeah, I don't know how you would. So I guess there's two questions. The particular matrix we defined, does it have a better? Well, so in fact, the particular matrix we define, I'm not sure we really know whether our bound on rectangle covering number is best possible. Maybe we didn't think too much about that, but I guess there's a possibility that you could do some better extremal set theory there to improve that bound. And of course, that means we also don't know whether other notions of for instance, hyperplane separation stuff would give better bounds. And also, of course, there's a question of whether you can construct completely different examples for which the hyperplane separation thing is better, which I think would also be very interesting, and which I don't have that much to say about.
Thanks.
Any further questions? So maybe just, but I guess this is a completely dual approach. So if you have a random polytope, say, and you would be projecting it to a fixed dimension, so sort of all sorts of projections. Is there anything interesting you could say about these numbers you would get in, different projections? Or maybe not even a random polytope, like you just have a polytope and you are projecting it. But yeah, of course, this is now completely from the opposite direction, right?
Sorry, so what's the specific question? So
well, like how much would it? Okay, so say take a polytope in dimension D and project it to dimension 2 or 3 or something, and do all possible projections, and whether you can say something about how much fluctuations in some sense you have in these different projections.
Yeah, so that does sound like an interesting type of question. I'm afraid I've got no idea whether that sort of thing has been studied, or I don't really have anything to. Certainly, I don't think that the stuff that we've done.
Yeah, sure. I understand that this is quite dual.
But that is, yeah, that's an interesting type of question, for sure. Yeah, there's this enormous literature on random polytopes, and I don't know whether this is the kind of thing they may have considered there, perhaps.
Mhm.